Ostwald. Oh, there's a lot of like weird names.
Let's start. Okay. If you have a stapler, you can staple it now. If not, you can do that later. Because I just printed it in the example. Yeah. Okay. So this is the order of the pages. So Haber process first, and then the Ostwald process on the next page, and finally making of virtualizer on the last, making of maximum on the last page. So you can staple these two pages in order.
So you not upload the notes in like something like one Wednesday. We not upload. You not upload.
Oh, I have it.
Yeah, you have it.
I have it. Well, I'll check. Okay, cool. Okay. And so let's start. Haber process is the part that we discussed last time. Okay, so it forms ammonia from nitrogen and hydrogen. So this rectangular box on top is for you to fill in this equation. Okay, so can you all fill out this block in here by inputting this equation? And also you don't have to memorize the specific delta H. I can't remember it either, but it's fine. Okay, so just remember that it's exothermic. You don't need to know how exothermic it is. Alright, but then the condition you have to memorize, and I'll put it down for you already. And under the conditions, okay, 450 degrees C, okay, 200 atm, and finely divided. Can you? Yes. Okay. So can you underline the term finely divided, and explain why this is done? Okay. So this is to increase the surface area of the catalyst. So adding a catalyst, will boost the rate. But adding a finely divided catalyst will boost the rate further because you have an even larger surface area. So this is why we use finely divided iron catalyst for the Haber process. And under the condition, you see I included a table. And inside the table, you see temperature consideration, pressure consideration, and catalyst consideration. So why do we use this temperature? Okay, 450 degrees C. Let's put that one. So temperature consideration. This is because the forward reaction, can you put down, is exothermic. So you have exo here. And the backward process must therefore be endo. Because forward and backward reactions, they have opposite but equal enthalpy change. So you have N2 and 3H2 reacting to give 2NH3. So do you remember how we can shift the equilibrium by changing temperature? When we increase temperature, which reaction will be favored? When we increase temperature, we will favor endothermic. Okay, so you can put that too high a temperature will favor endo, which is not what we want. So can you put on, you see I included an arrow here. In the middle of the arrow, can you draw a vertical line, a very short vertical line, and write down 450 there, okay? That's because if you use a higher temperature than 450, it will favor, so higher temperature, you have to write this inside the box, so try to write really small then. So higher temperature than 450 will favor the endothermic reaction. We learned that in the equilibrium chapter. And what will this do to the yield of ammonia? Does it increase or does it decrease the yield of ammonia? Decrease. So therefore we don't want that. We don't want any temperature above 450 because of that. So therefore, decreasing the yield of NH3. So this is bad. To avoid this happening, we want to use a lower temperature. But why can't we use an even lower temperature than 450 then? Well, that's because we have another concern. Okay, so lower temperature should favor exothermic reaction. But there's a downside to doing this. So you can write down lower temperature should favor the exothermic reaction. And therefore, it should increase the yield of ammonia. But why don't we use 0 degrees Celsius then? Or to make it worse, why don't we use a negative temperature instead?
The reaction will be very slow.
Yeah, very slow. Okay, so we are concerned about not just the yield, but also the rate. Okay, so can you take out a highlighter and highlight these two things? This we mentioned in the equilibrium chapter. To a chemist, both the yield and the rate are important. You don't just try to boost the yield. You have to also boost the rate. If the reaction will produce a very high yield, but then the rate is very low, okay, it is still a useless reaction. So therefore you can say, but, okay, rate would be too low at such low temperature. So underline the word rate and yield, okay, at such temperature. So therefore this is not preferred, okay? And as such, we use 450 degrees, and that's what we call a compromise. So a compromise means we have considered like the pros and cons, okay, of using a higher and lower temperature, and we settle with 450. This is what we finally settle with, is 450 degrees. We call it a compromise, okay? So everybody should know what the word compromise is. And so that's the temperature consideration. On the side, we have also, so any question about the temperature consideration? No, okay, yeah, you can treat this as like a recap, okay, or review of the equilibrium chapter. So you can refer back to equilibrium, the videos, okay, if you forgot about this. But then, what about the pressure consideration? How many gases are there on the left hand side and on the right hand side of the equilibrium? Do you see? There are 4 on the left.
Oh,
Yeah,
right.
1 plus 3 is 4, and 2 gases on the right. Okay, so maybe you can add this also to this rectangular box. Yeah, where you wrote N2 plus 3 is 2. You can throw a bracket on top like I'm doing now and write 4 gas molecules or 4 gases. On the right, we have 2 gases. We only look at the mole ratio. We only add up the mole ratio. So the pressure consideration is that we have 4 gases on the left, becoming 2 gases on the right. So in the equilibrium chapter, we learned that when we boost the pressure, okay, what will happen to the equilibrium? To which side will it shift? Will it shift to the side with more gas or fewer gas when we increase the pressure? Fewer, okay, so therefore can you put down increasing pressure will make it go this way, decreasing the pressure will make it go this way. So therefore you can put down higher pressure than 200 atm should shift the equilibrium to the fewer gas side, okay, so fewer gas side, which is this side. And therefore, it should boost the yield. So the yield of ammonia should increase. But why do we not use a pressure above 200? That's because it's costly, okay, to build such a strong container that can withstand a high pressure than 200. You know 200 atm is a really high pressure. 1 atm is the pressure we are experiencing right now. When you have a column of air sitting on top of you when you're outside or when you're indoor, that is what is putting pressure on you. That's not much of a pressure, right? So 200 atm is like many elephants sitting at the top of a pinhead, and that pinhead rests on your head. Okay, that's how much pressure that is. And you have to use a lot of money to build a container that can withstand that high pressure. So it's simply not worth it, and it's dangerous. So therefore, you can write down, but it's expensive and dangerous. Okay, to build a container that can withstand such a high pressure, so that can withstand. Yes. Okay, quickly, please. Okay. So that can withstand such a high pressure. So what about lower pressure than 2 atm? Why is it not ideal then? Well, that's because when you lower the pressure, we will favor is it the forward or the backward reaction this time? The backward. So therefore, you can put down pressure lower than 200 atm will shift the equilibrium to the more gas side. Remember, it is the product that you want, not the reactant. So it makes perfect sense why you don't want to use a lower pressure than 2 atm to the more gas side. So therefore, yield would decrease. Also, rate will decrease because the pressure is now lower, okay? So rate also decreases when the pressure lowers. So also decreasing. So this is bad, okay? Pressure lower than 200 atm. And then we have the calculus consideration. So why do we add a calculus? Is it because we want to boost the yield, or is it because we want to just boost the rate? We want to boost the rate. We want to get to equilibrium more quickly. Okay, so we use a catalyst. So, and you notice that I did not put an arrow here. Well, that's because for catalyst you can either just add it or not add it. Okay, you would just add it or not add it. So here, can you just draw a graph in there? So it's catalyst, consideration, and you can write down catalyst will increase the rate of both the forward and the backward reaction. So forward and backward reaction, and it will not increase the yield. Okay, triple underline or quadruple underline, it will not. Okay, so I don't want you to say catalyst increase the yield. It will never increase yield. But it will help you get the same amount of product in a shorter period of time, which is still worth it. Okay, so it will not increase the yield of product, but you can get the same amount of product in shorter time. Okay, and you see I left some space in there for the catalyst consideration graph because I want to ask you all a question. So you can finish copying this first. So these are the two things catalysts will do. And any question about temperature consideration and pressure consideration? No. Okay. And when you're done, you can draw a graph in the catalyst consideration box. If you don't have enough space in there, you can use the space right under the rectangular block. Okay, there's still a little bit of space. So you can draw a graph there, please. So you have nitrogen and hydrogen. So this is what happens if you do not add a catalyst. So this is the nitrogen and hydrogen, and this is ammonia. Do you remember some features of a dynamic equilibrium? What will happen to the concentration of all species when you reach equilibrium? Do the reactant concentration become equal to the product concentration, or will the reactant concentration and product concentration just remain constant? Remain constant. So therefore, don't you merge the two lines. Okay, I mean they can become equal, but that's just a coincidence. Okay, that's not an absolute must for when you reach equilibrium. So if this is the graph you ought to draw, label the axis for me, please. This is concentration, and this is time. Yeah. Okay. Or maybe you can draw a separate graph for hydrogen. Okay. Because hydrogen, the mole ratio is 1:3 between nitrogen and hydrogen. Hydrogen should be used at a faster rate. So you see a graph that looks like this. Can you show me what would the graph be like if I add a catalyst? So this is without a catalyst. And I wanted to overlay on this diagram another 3 new curves that describe what will happen with a catalyst. Just ask yourself, what does a catalyst do again? It increases the rate, right? How does rate appear in a concentration time graph? What in a concentration time graph represents rate? The slope or the gradient, right? So can you multiply this graph? Can you draw 3 new curves on this graph? That will show what happens when I add a catalyst. Remember, the gradient represents rate. And you know catalyst increases the rate. It makes the graph, it makes the curve steeper. Can you draw 3 new curves here that will reflect that? I don't want to just give you an answer because I don't want to think. Okay? Increasing rate means making the slope steeper. So how will the graph change? So you have 30 seconds to draw this. And write down this point on the side, please. Note the slope of the concentration time graph is rate. And you know catalyst increase rate. It means it will make the graph steeper. So anyone have an answer here? How should I draw the graph? Any idea? No. It will be steeper. All the graphs will be steeper. So for the N one, it will be like this. For the hydrogen one, it will be like this. For the ammonia one, it will be like this. Why would all the curves still merge at the same point? Because the yield is not changed yet or the same. Okay, so you will only change the slope of the initial portion of it. Is this clear? This is what happens if you add a catalyst. Do you see that you reach equilibrium in a shorter amount of time? Yeah, so how long does it take to reach equilibrium before you add a catalyst? This is how much time it takes before all three curves plateau. This is the time it takes to reach equilibrium without catalyst. And how much time do you need to reach equilibrium with the catalyst? Do you see that you reach equilibrium sooner rather than later? Okay, so this is what I meant here. Okay, I think this is a very powerful graph that will show you these two features. Remember, rate means slope. So the blue curves, they are all steeper than the red curve. The yield is not changed. So they finally end up at the same point. Is this clear? So, let's move on. Now that we understand the choice, okay, of these three conditions, we can now look at how we can obtain the raw material, okay, the chemical feedstocks, okay, for this reaction. Nitrogen and hydrogen. Okay, so you can copy that later, don't worry. And we'll now look at the reactants, okay, obtaining the reactants. Okay.
Oh, you're trying to arrange them.
Yeah, you can refer to the bottom part of the notes right now. About hydrogen. Okay, so we have hydrogen in here. H2. There are 4 different ways to make hydrogen. But hydrogen is not a part of the atmosphere because it's very light. Okay, remember what are the 2 most abundant gases?
Nitrogen and oxygen.
Nitrogen and oxygen. Yes, hydrogen is not in the atmosphere because of its lightness. Okay, it will just go into space. Yeah, and we can make hydrogen by 4 methods. So method 1, we call it steam methane reforming. So steam is of course H2O gas, methane is CH4. Yeah, reforming means you rearrange the atoms in a new way to form the product. So you have CH4 plus H2O. So I have saved you the trouble of copying this equation. I have typed it for you already. So it's methane and steam reacting to form carbon monoxide and hydrogen. What you need to know is the conditions I put on this rectangular box on the side. So I have put down all the conditions in here. So there are 3 to 4 different set of conditions you should remember. So this is specific to this particular reaction. So 7 to 1000 degrees C, 10 to 20 atm, and can anyone name this catalyst? Nickel
Oxide.
2
oxide.
oxide. Because nickel is it an ordinary metal or a transition metal?
Transition.
Transition metal. So can you put down the name? Nickel 2 oxide, as this is a transition metal. So I intentionally left this out. Left out the name because I want to ask you this question. So this is transition metal, so you need the Roman number 2 here for most transition metals. But for zinc and for silver, you don't need to include that number, remember. You never say zinc 2 oxide, silver 1 oxide, because zinc and silver only form one particular ion. But nickel can form more than one ion, so we need to do this. So the second reaction, by the way, if you have a highlighter, okay, can you highlight these 2 products? Together, CO and H2, they are known as syngas. So syngas means synthesis gas. Okay, so synthesis gas. But I like to just remember the shorter form whenever possible. So just remember it as syngas. And syngas is a raw material for making methanol, as you will see on the last page. Okay, the very last page of these notes. So we have another reaction that is quite similar to the steam reforming reaction. Oh, and by the way, can you tell me which species is oxidized and reduced in this reaction? What is oxidized? I hope you don't answer this wrong.
Carbon.
What is oxidized and what is reduced in this reaction? What is oxidized?
CH4.
CH4 is oxidized. Okay, don't say CO is oxidized. Okay, so can you put down CH4 is oxidized? What is reduced then?
H2O.
H2O. Okay, so and to save you time, I'll just put down the oxidation number for you. H oxidation number went from +1 to 0. C's oxidation number went from -4 to +2. So make sure you verify that later, okay, to see if it's actually a redox reaction. So this is redox. This is a redox reaction. Next, we have another reaction similar in nature to steam methane reforming. It's called a shift reaction. So in a shift reaction, we have carbon monoxide reacting with water to form carbon dioxide and hydrogen. This time around, what is oxidized, what is reduced?
What is being oxidized?
What is oxidized?
CO.
CO, yes. So carbon monoxide is oxidized and water is again reduced. Okay, again put down the oxidation number to see it for yourself. +1 to 0 for hydrogen. And +2 to +4. Okay, so that is like an oxidation reaction going on. So this is what you should know. And can you circle the product? We do these reactions because we want to make hydrogen. The hydrogen can then be used in the Haber process. We need to get some hydrogen. Okay, so this reaction will help us get some hydrogen. Okay, so we have the third reaction. Okay, that you will see later. Oh, you have learned this in Form 4, back in Form 4. Electrolysis of brine. Right, brine. Brine means seawater, okay, which is basically a concentrated solution of sodium chloride. So electrolysis of brine, okay. So we will look at this later on page 4. Okay, yeah. So therefore here, just allow me to touch on this very lightly. Yes, 2 NaCl concentrated aqueous solution plus 2 H2O will give 2 NaOH plus hydrogen and chlorine. Can you circle the hydrogen? Because hydrogen is one of the products, we can use this reaction to make enough hydrogen for use in Haber process. And last but certainly not least, we have cracking. You see I wrote 4 general equations here because I'm not sure if you know that cracking can produce a number of products. It can produce alkane, it can produce alkene, it can also produce hydrogen. So first of all, can you tell me what's the general formula of alkane and alkene respectively?
C and H2 and plus 2.
Yes, okay, put this down. First let me put down the heading. So cracking of long alkane. So and right on the on the right hand side of method 4, can you see some blank space? You can write down the general formula of alkane and alkene there. CnH2n plus 2 is the general formula of alkane and starts from 1. Yeah, you will know why I asked very soon. Alkene has a general formula just 2n. Okay, so it's alkene. Yeah, I'm just worried that they may ask you another homologous series. Okay, it's called alkyne. So while alkyne they did not really put it in the syllabus, you should know that they have triple bond.
-2.
Oh, very good. Okay, so maybe you got tricked before. So you
I
so
learned
this
this
stage.
before.
Okay, so it's CnH2n minus 2. To me, it kind of makes sense because one is 2n plus 2, the second is 2n plus 0, the third is 2n minus 2. Makes perfect sense, right? Alkane has CC single bond. Alkene has CC double bond. Alkyne with a Y. Okay, if this is new to you, if you think this is new to you, yes, because it's new. Okay, yeah. So this is a triple bond, and you cannot have anything more complicated than that because the most bond carbon can form is a triple bond. It cannot form a quadruple bond. Okay, so what must N start from for alkene? 2. Okay, because you must have at least 2 carbon for an alkene, right? You see alkene has C double bond. That means they must at least have 2 carbon. For alkyne, they must also have at least 2 carbon. Okay? So, first of all, I want you all to tell me what's the formula of the alkane with 10 carbons.
Alkene.
Alkane.
Oh,
with 10 carbon. C10 22. Okay, so you see 4 equations here, right? So like I'm not going to write down those words again. You see 4 separate word equations on your notes. For the first one, under that word equation, can you write C10H22? Becomes, now make a number, think of a number between 1 and 10.
5.
5. So what is an alkane and an alkene with 5 carbons respectively? C5,
12.
H12. What about alkene with 5? H10. H10. So this is one possible way in which a long alkene can crack. Yeah. What about the right hand side general equation? Can you double underline alkenes? You may think that it appeared twice, but this is actually short alkene singular on the left. This is short alkenes on the right. Double underline the word the letter S there, okay? So you have alkenes. Now we can crack this into something simply. So you can have a C2 alkene and a C3 alkene. Can you see that the math still checks out? 12 plus 4 plus 6 is still 22. So these are alkenes, okay, plural. But this is not what we want. We want hydrogen, right? So we continue. What about the third reaction here? Okay, so it should be short alkane and I think yeah. So the third one is actually the same one as the second one, right? So this is the same thing as this one,
yeah.
Or this one. So just ignore this one. Look at the third equation. So the third equation here. You can have C10H22 forming a bunch of alkenes. Can you give me 2 numbers whose sum is 10? And any number?
7, 3.
7 and 3. So C7H14 and C3H6. These are alkenes. Okay? And to make the math checks out, you need hydrogen. If you don't add a hydrogen here, you see 14 plus 6 doesn't add up to, they don't add up to 22. So can you circle the hydrogen again? Because when you do cracking, you cannot control how the molecule break. So that means when you crack the same molecule, that king, these 3 are that king. Okay? You will end up getting a mixture of many products, one of which is hydrogen. You can't control how the molecule break, which is why just now I asked you to think of a number between 1 and 10. Because in the industry, when you actually crack that cane, yeah, it's a random process cracking. You will crack the molecule like anywhere, okay, in one of those CC bonds in there to form many products. One of the products you see is hydrogen. Okay, so this is one last way to make hydrogen. So you may think, well, so much for just hydrogen. Well, for nitrogen, the concept is a lot simpler. But any question on how we make hydrogen first? There are 4 ways to make hydrogen. Okay, you need to know them all. Okay. Next up, we have nitrogen. How do we make nitrogen? This is just a recap on what you learned in Form 4, really. So nitrogen is obtained by fractional distillation of air, from the fractional distillation of air. So it's obtained from the air by fractional distillation. However, you see I left some space in there for you. That's because I want you to
Write down.
draw something. So draw 4 boxes for me, please. So 1, 2, 3, 4. What are some things that you can find in air? Oxygen.
Carbon dioxide.
Yeah, and carbon dioxide, and then
Argon.
and finally nitrogen.
Oh.
Yeah, and also water. Okay, you forgot water. So we have nitrogen, carbon dioxide, oxygen, argon, and water. So first of all, before we can do anything about air, we need to cool it down to extremely low temperature first. Okay, so this is cooled to low temperature. You don't have to remember the temperature. Okay, that's not the important point. The important point is that 2 substances, they will settle out as solid. Can you guess what they are? Which 2 substances of these 5 substances we just mentioned in the air will solidify?
Argon?
No. Argon is very difficult to solidify. It can only be liquefied. It cannot solidify. Carbon dioxide. What do you call solid form of carbon dioxide? Dry ice. You know, dry ice is a solid, right? So we remove CO2, and there's another thing, there is actual ice, water. Okay, water is also removed. Okay, so CO2 is removed as dry ice, H2O is removed as ice. We want to remove them because it is nitrogen that we are after. Okay, we are not trying to make carbon dioxide and water. We already have enough of it in the ocean. We don't need to get it from the air. So they are just removed. We are inviting them to leave. Okay. So now you will have, like when you cool it to low temperature, you will now have liquid, nitrogen, oxygen, and argon left. And now I need to show you the boiling point. I couldn't remember the boiling point, and neither should you. Okay, so you can just refer back to in here. You just find the air component boiling point. So, okay, this is a rather nice diagram here. Okay, so can you copy these boiling point in here? Because when I asked the Form 4 question, Form 4 student this question, they struggle a little bit. So the boiling point of oxygen is -183. Of nitrogen is -196. This will be provided to you if they really would ask you a question about this. So argon is -185 degrees C. My question is, if we cool the air down to -200 degrees C now, can you tell me what happens if I slowly raise the temperature back up from -200? Which of these gases will boil off first?
Will boil off first.
Will boil off first as I slowly raise the temperature back up from -200. I raise it back to room
Argon.
temperature. Which gas of these three will boil off first?
Argon. N2.
So something N2, something argon. So which is the correct answer? It's actually N2. Because what is the next closest number to -200? -196. Can you draw a number line?
196.
Yeah.
Yeah.
So to students who may
Oh, it's
have
not
trouble with this question,
I thought
I-
it's like one.
I suggest that you draw the number line. Can you draw the number line, please? And arrange these numbers back in order. Then the answer will come to you. Okay, let's try this. -196 comes right after -200, right? What is the next closest number?
185.
-185. Okay, and finally -183. So this is what we are doing now. Okay, and so can you put down -196? As soon as we warm, -200 degree air into -196, something will come out of the liquid air. So this is liquefied air. So this is liquefied air. The gas, nitrogen, will boil off first. So you see nitrogen escaping? Yeah, you can collect it. Okay, and can you circle nitrogen? This is what we collect for the Haber process. Yeah, what will continue to dissolve in the liquid water, liquid air? Yeah, argon and O2. So we are not done. Okay, we can continue to, remove the gases slowly. Then we slowly warm it again. This time to -185 degree. Which gas will boil off next?
Argon.
Argon. So now you have only oxygen left. It's rather lonely in the liquid air now. So the argon will boil off, and eventually you will also get pure oxygen from it. Okay. So this is what we mean by fractional distillation of air. So I suggest you understand it this way. Because to boil a substance, like you need to reach the boiling point of that particular substance. So you're slowly raising the temperature back up. Okay, and because some students they may have trouble, handling the negative number, so I suggest you draw a number line to see the order more clearly. So can you put down a quick summary? And it is that nitrogen boils off first, followed by argon and oxygen. Okay, so this is the order. If you like to remember it, you can use NaO like now, like NaO to remember the order. NaO. Okay, yeah. So that's just the unit that you use. So that's how we obtain nitrogen, and we are done with this method. But on the next page, we have a very, very complicated graph to analyze. Okay? So once you're done with this page, I want your attention on the next page. Okay. But any question first?
Boy what?
No.
No, boy off.
Boys off first. Boys off first. Yeah.
Okay.
Boys off first. Now, when you're done, can you turn to the next page where we look at the effect of this page with two graphs on it. The effect of temperature and pressure on ammonia yield. So, and this is not a mistake. I know the two graphs look the same because they are, okay? Can you take a look at the y and the x-axis? The y-axis shows you the percent yield of ammonia. The higher the better, of course, okay? And the x-axis shows you pressure, okay? And then you don't see another axis, okay, with temperature on it. That's because the temperature, information is available in the form of different curves, okay? So I'll draw this, let me copy this on the side first. So you have several temperature here, right? You see, you have low temperature. So I'll just draw two graphs in here. This has a lower temperature, and this has a higher temperature. If you like, you can also reduce this graph to just this simple diagram. So the higher the temperature, the shorter the curve, okay, and also the less steep the curve. You can reduce this diagram into a simple diagram like this one. Yeah. Can you tell me what should we control when we study the effect of temperature? Should we also change pressure when we study the effect of temperature?
No.
No. So therefore, it's up to you now. You can fix a particular pressure. So draw a vertical line any way you like on this graph. Yeah, if you can draw it here. You can draw it here, or it doesn't matter. Just pick a random pressure. I will draw it here. Okay? So draw a random vertical line here anywhere. So to study the effect of temperature, we fix pressure. Write down the sentence to accompany this. To study the effect of temperature on yield, we fix pressure. Because that's what you learn in Form 1. Okay? When we study the effect of one factor, we keep all other factors unchanged. Okay? So when we study the effect of temperature on yield, we should fix pressure. Okay, so we should fix pressure. Keep it unchanged. So this is how we fix it. And then we look at how changing temperature would affect the graph. Can you tell me at this pressure, what happens when you increase the temperature? So when you increase the temperature from low to high, what happens to the yield? It decreases. It decreases. Yeah, when you go from low temperature to high temperature, do you see that the yield, the associated Y value, also decreases, right? That's the conclusion you can draw. This one, for this one. Right now, point 1 and 2. Point 1 here states that when we increase temperature from low to high, okay, you can use some colors to help. Okay, so from low to high, from the blue to the red curve, what happens with the yield? The yield of ammonia decreases. Yeah, this aligns perfectly with what we described earlier. The Haber process is an exothermic reaction, right, in the forward direction. So it makes perfect sense that increasing temperature would lower the yield. Because increasing temperature would shift the reaction in a way to favor the endothermic reaction, the backward reaction. So it makes perfect sense that you drop. So, and this is done. Okay, yeah, this is what we should be able to conclude from just this graph about the effect of temperature. To study the effect of pressure, we take another approach. Okay. So on the left, let me put down the what we are studying first. The effect of temperature. Now on the right, we are studying the effect of pressure. Just like what we did just now. If we want to study the effect of one factor, what do we do to all other factors? We keep them constant or unchanged. So can you write down the same sentence here before, like before? to study the effect of pressure on yield with fixed temperature. So how do we fix temperature in this particular graph then? Well, we select a particular curve. So you can pick a favorite curve of yours. If you like the, I don't know, maybe if you like the 400-degree curve, just maybe make it bolder. We will just look at one particular temperature. We are not going to change temperature now when we study the effect of pressure. So just select a favorite temperature of yours. I will pick this one. I will pick the 400-degree Celsius one. Any graph will do. The explanation will be the same, trust me. So to study the effect of pressure on yield, we should fix temperature. Okay, so let's do this. We have fixed temperature, so we have lost our eyes on this curve. Can you tell me what happens when I increase the pressure? When I increase the pressure, what happens to the yield? As I increase the pressure from this value to this value, what happens to the associated Y value? It increases, right? You see? Yeah. So from this particular pressure to this pressure, the yield increases. So put down a conclusion. So number one, when we increase the pressure from low to high, so this is low pressure, this is high pressure. So from low to high, the yield of ammonia increases. Okay? So again, this is completely in line with what we learned on the previous page. Do you remember why? And you can refer back to the pressure consideration here. Because there are more gases on the left-hand side of the Haber process than on the right. So increasing pressure should push the yield because it will push the reaction to the fuel gas side, right? So this is just a graph to support what we explained on the previous page. Yeah, that's only one job. Okay? So that's one page. Okay? Any questions so far?
No.
No. Okay, so for this graph, therefore, you can't be greedy and look at everything at the same time. If you look at everything, you don't get anywhere. Okay, you have to know what you're looking for. If you are studying the effect of temperature, just forget about the pressure. Okay, just look at the temperature. When you change the temperature, you see the pressure, the yield changing. But when you study the effect of pressure, you forget about the temperature. Okay, so you fix just one particular temperature and you study the effect of yield. So that's about the graph here. Then we'll move on to the next page. Yeah, so remember if you have a stable, try to stable it. So the next page is the Ostwald process, okay, which makes nitric acid. It makes HNO3. Okay, so we'll try to do that now on the opposite side. So let me write this. Ostwald process. So we have Ostwald process. Unlike the Haber process, it is not a single stage reaction. Do you remember the Haber process has only one reaction? It's N2 plus 3H2 becomes 2N3, that's it. Nothing else. So for Ostwald process, it's actually a sum of 3 reactions, which I have put down for you. The first one is called the oxidation of ammonia using air. So can you put down? It's a 3-stage process. So stage 1 is oxidation of ammonia. So this time I want to do the question differently. I want you to tell me what is oxidized and reduced and explain your answer using oxidation number. So you have 30-second talk, okay? Find me the oxidation number of these substances. And then use that to explain to me whether they are oxidized or reduced, okay, in the process. What is oxidized, what is reduced? 30 seconds, okay? So you should put this inside that rectangular box on this page. There's a long rectangular box on this page, right under oxidation of ammonia. Put this equation in. So ammonia comes from the Haber process. Okay. So we're building on what we learned. We already know how to make ammonia. So what do we do with the ammonia then? We can use the ammonia in the Ostwald process to make nitric acid. Okay, so we are on this page. Can you put down this equation in this rectangular box? And 30 seconds to figure out what is oxidized and reduced. Support your answer with oxidation number. Yeah, you just have to find the oxidation number of the underlying substance. Remember that elements must always have oxidation number equals 0. So O2 you don't even have to calculate 0. Elements always have oxidation number equals 0. The other you need to calculate using the fact that H prefers to have an oxidation number of +1 in compound. O prefers to have an oxidation number of -2, except in hydrogen peroxide. What is the oxidation number of O in peroxide? -1. Remember. Okay. So put down this if you forgot the redox chapter. So in redox, we learned that certain atoms prefers certain oxidation number. Okay, certain oxidation number in compound and ions. So I have to stress this. Only in compound or ion do they prefer certain number. Because in element, they must be 0. Okay, they must be 0. So can you put down what those are? H prefers to have an oxidation number of +1. O prefers to have an oxidation number of -2, except in peroxide. So except in peroxide, such as H2O2, where O will be -1 instead. And finally, you have halogen preferring an oxidation number of -1. X is Cl or F or Br or I. Okay? Now this you need to recall from the redox chapter. Okay, so this is what it is. So time's up. Which substance is oxidized? Which substance is reduced? And I need an explanation.
oxidized.
Why?
Oxidation number goes from -3 to -2.
To
+2.
+2. Yes. So can you put down ox here? So we say NH3 is oxidized. Don't say NO is oxidized. NO is not oxidized. NO is what is produced in the oxidation reaction. So this is oxidized, NH3. So O2 must be reduced because the oxidation number went down from 0 to -2. So this is reduction. Good. Okay, that's it. And this reaction, okay, you also need to remember the condition. Okay, so can you put down the condition here? Oh, by the way, this should be a reversible reaction like that. Okay, so this is a reversible reaction with the following conditions. Yeah, it's it's 900 degree C for temperature, 8 atm for pressure, and this time the catalyst is platinum. Okay, so it's platinum. Right. So this reaction, you can say it makes NO for our second reaction. So this would go to step 2. Okay, so the step 2 here is the oxidation of NO. Yeah, by air. So you have NO plus oxygen becomes NO2. Yeah, so you have NO2. So you get NO2 in here. And, okay, so, oh, I forgot to balance this equation. Can you put this down? 4, 5, 4, 6. Quite easy to remember. 4, 5, 4, 6. Okay, so the number. And, okay, after we oxidize the NO, here, let me ask you a question. What are the colors of NO and NO2? Remember, they are both pollutants. What is the color of NO?
Yellow.
Colorless. What about the color of NO2?
Yellow.
It is brown. Yes, okay, so it's brown. So this is colorless. And this is brown. So what is the connection to other chapters? Do you remember the oxidation property of nitric acid? When you have dilute nitric acid and concentrated nitric acid, when you use them as oxidizing agent, the products are different. Can you put down this equation? I want to, do some cross review here with you. When you react copper with dilute nitric acid, compared to when you react copper to concentrated nitric acid, what will you see in the test tube?
CuNO4O3. NO3 2.
CuNO3 2 and
H2.
yeah, so CuNO3 2 is common to both reactions, but then the gaseous product are different.
The below one have NO2.
Or
Or
even
NO.
the bottom one has
The
NO2.
bottom one is
The top one has only NO, okay, and there will be H2O.
Oh.
So how do you know if, let's just say I have two test tubes here. I'm not telling you which has dilute nitric acid, which has concentrated nitric acid. And if in exam, they ask you to describe a test that will help distinguish between these two unlabeled test tubes. So note that I'm covering the labels. You don't know which is which.
Yeah.
So you can just drop a copper strip into these two solutions and observe, okay, what is produced.
Sir,
I thought copper will not.
copper will react with acid though, right?
No, the
Copper
dilute.
will not react with normal acid like
Oh.
HCl, but copper will react with nitric acid because nitric acid is not reacting using the acid property. It's reacting using the oxidizing property.
Oh, okay.
Yes, yeah, and I'm glad you asked, okay. Do you remember that copper should not react with normal acid? By normal acid, I mean HCl and dilute H2SO4. Yeah, oh, this reminds me of the acid base reactor. Oh, this is a really nice question. Can you put down dilute HCl, corn HCl, dilute HNO3, corn HNO3, and dilute, okay, I think it's more, efficient to put the terms like this, okay? And we have two more acids, dilute H2SO4 and concentrated H2SO4. On the right, maybe you can guess what I'm doing next. I'm going to put acidic property. Acidic property means whether they have H plus, okay? So they have H plus. Do they all have H plus?
Yep.
Yeah, of course, right? So they are all acids. Okay, so they have everything in here. Yeah, but then we have the second property is oxidizing property. So only how many of these acids have oxidizing property? Do you know? Actually, 3. They are corn sulfuric acid, corn nitric acid, and dilute nitric acid. So the rest do not have oxidizing property. Yeah, and finally, we have the dehydrating property. Well, this you must know. All of you must know. Only only corn H2SO4. Okay, so can you remember to revise for this table? Dehydrating property, sorry. Yeah. Which reaction in organic chem? I'm sorry, I have to ask you this the millionth time now. What is that reaction in organic chem that would use corn sulfuric acid as the dehydrating agent? Yes, the dehydration of.
Alkene?
You cannot dehydrate alkene because they do not have O.
Oh, carboxylic.
No, it's alcohol.
Okay.
Do you remember? Okay, let me remind you from a million pages ago. Where was it? I have trouble finding it, but just a moment. It's here. Do you remember that you can dehydrate alcohol using corn sulfuric acid? Okay? Yeah, so I hope if they really ask you this in the SE, you remember. The dehydration of alcohol, okay, with dehydrating agent, corn sulfuric acid. So can you put down just one tick in corn sulfuric acid? Okay? And put down a star next to the acidic property. Because copper, okay, while it doesn't react with ordinary acid, it can react with dilute HNO3, corn HNO3, and corn sulfuric acid. So just put an extra point in here. So copper, okay, does not react with dilute HCl or dilute H2SO4. But it reacts with the other acids, dilute HNO3, corn HNO3, and corn H2SO4 because of their oxidizing property. Okay, so they are reacting with copper using this property called oxidizing property. Okay, so this table I know may be very difficult to remember. So maybe I'll just put away, remove the process. They're just making it more complicated. So only 3 acids have oxidizing property. only one has dehydrating property. And all of them, of course, because they have excess, they have acidic property. Okay? Back to here. How do I distinguish between them then? You know, NO is a rather strange gas. Okay, while NO is colorless, when it comes into contact with air, it will also be oxidized. So therefore, for the first reaction here, when copper reacts with dilute HNO3, you will first get a colorless gas at the mouth of the test tube. But this colorless gas will eventually turn brown because there's oxygen in the air. And the oxygen can turn the NO into NO2. So this is by the O2 in air. But the thing is, you don't immediately get a brown gas with this reaction. But when you use concentrated HNO3, can you see that the product is NO2? Yeah, that means immediately you get a brown gas on top of the mixture. You don't have to wait. Do you see the difference? Yeah. You may think it's a very small difference, but this difference is enough to distinguish between them. Is that clear?
Yeah.
Okay? Yeah, this is another question they will ask you. Okay, now back to the Ostwald process. Stage 3 of Ostwald process is the dissolution. Okay, if you really hate this word, just change it to dissolving. Okay, the dissolving, okay, of nitrogen dioxide using air and water. So write down step 3 here. Step 3 is the dissolution of the NO2. Okay, so NO2 plus O2 plus H2O gives HNO3. Okay, so you have HNO3. So how many? So we can put the 2 in here because there are 2 H's in here, and we have 6 O. Okay, so you have how many O2 will be needed then? You have 6 O on the right.
3.
And currently, how many O do you have on the left?
5.
You have 5.
1 or 2.
So you need to put, you actually need to put 2, 3, and this should be 3 over 2. So 3, 5, 6. Yeah, like that. But then of course you will think, wait a second, we are not allowed to use a fraction or ratio, right? So we can just multiply everything by 2. So therefore, making the final equation 2NO2 plus 3O2 plus 2H2O becomes 4HNO3. So I'm telling you this because I don't want you to always just memorize the equation. If you can balance it, just balance it, okay? And then you can of course write down like a fractional ratio at the beginning and later change it back to whole number. Okay, there's nothing wrong in doing this. Okay, because I hate memorizing equation. I always work them out from scratch like this. Okay, this solution of nitrogen dioxide. Can you put down air and water? So you need air and water for this reaction. But what about for step 2? Do you need air or water or both for step 2?
Air.
Air only. Can you put down air back to step 2? So for step 2, you only need air, you don't need water. And for step 1, you will also need air. Okay, so this is why I put down in here, the oxidation of ammonia uses air. The oxidation of nitrogen monoxide uses also air. And finally, you use both air and water. Okay? So now, okay, we are making good progress. Let's take a look at how we can make fertilizers. We already discussed fertilizers at the beginning of this chapter. Okay? So fertilizers, also known as nitrogenous fertilizers because they contain nitrogen, they help replenish nitrogen in soil. So we have nitrogenous fertilizers. There are 3 types. Ammonium nitrate. So now I need all of you to work on this. Only the first 2 because you might not know urea unless you do biology. Right? Even if you do biology, you may not know its formula. Can you tell me what's the formula of ammonium nitrate and ammonium sulfate?
Ammonium nitrate, NH or NO3.
Yes. What about ammonium sulfate?
NH4
SO4.
Yes. Okay, good. Very good. So make sure the rest of you know how this formula is obtained. So write this down first. Ammonium is NH4 plus. Nitrate is NO3 minus. So when you do the crisscross rule, you get ammonium nitrate, NH4NO3. Ammonium ion, continues to be NH4 plus. But sulfate is how many minus? 2 minus. Yes, so 2 minus. So when you do the crisscross rule thingy, you get NH4 bracket, okay, must be there. NH42SO4. The last of all the common nitrogenous fertilizer is urea. Okay, so for urea, I prefer drawing the structure. So it's CO with 2 NH2 group on the side. What do you call an NH2 group?
Amine.
Amine. Yes, with an N. Okay, yeah, but you can argue that this is like an amine because it has a con, C-O-N. Okay, so it has C-O-N. But if I just refer to the NH2 group, it's an amine group. So this is urea.
So this is amine or amine?
So this should be an amine, you can say,
Amine.
because it has con. Okay, and what is the class of this amine?